I'm pleased to say, Sergio, that Boreal Laser has enjoyed very fruitful strategic relationship with Shell entities, both domestically and internationally, over the last 10 years. And as I will show in my presentation today, we're working on a number of exciting new developments in conjunction with Shell Global Solutions within the Shell organization. I have far too many slides here to cover in 15 minutes, so you will excuse me if I pass over 2 or 3 of them in the process without even addressing them. As Sergio said, Boreal Laser is an Edmonton-based company. We've been making laser-based gas detectors since 1996. We use a technology called single-line absorption spectroscopy, operating in the near-infrared. And today we have installations in over 40 countries worldwide. And we are a world-leading supplier of open-path laser gas detection technology. The reason, or the way that what we do fits into the umbrella of micro and nanotechnology is that the basic analysis, the basic measurement engine in our systems is a tiny little semiconductor diode laser, which emits laser light that is of the order of microns and multiple nanometers in wavelength. This is a montage of different products that we manufacture and sell, and just briefly describe what it is that we do. Inside an instrument such as our GasFinder 2, there is a semiconductor diode laser which is manufactured to emit laser light at a wavelength that is absorbed and only absorbed by a target gas of interest within the measurement path. So by shining that laser light through the ambient air to, for example, a reflector array that shines the light back to detection electronics inside the instrument, we can determine the amount of that target gas of interest that is in that ambient path. That ambient air path could just as easily be a path within a stack or within a process. It's not a technology that is exclusively used for ambient air monitoring, but what it is a non-contact spectroscopic technique for determining the concentration of a specific gas within an assembly of different gases. I'll just briefly go through this slide here. As I will describe later, one of our major areas of research and development right now is to move more into the mid-infrared and away from the near-infrared. Operating in the near-infrared, as we do currently, we're restricted to making measurements on relatively small molecules. We have to move into the mid-infrared before we can start targeting those potentially more exciting and interesting polyaromatic hydrocarbons, volatile organics, and compounds like that. A lot of our work is in refinery and petrochemical leak detection applications. We've done a lot of work in recent years with greenhouse gas monitoring from landfills, agricultural operations, and most recently, as I'll describe, from proposed carbon capture and storage projects. The title talked about quantitative measurements. This configuration shown here is one device that we use for making quantitative measurements of fluxes of specific gases from area sources. This area source could be a landfill, it could be a refinery, it could be a gas plant, it could be a tailings pond, for example. The GasFinder instrument is mounted on a programmable scanner and can successively send the laser beam to multiple reflector arrays. And from that process, we can build up a matrix of path-integrated concentrations for a number of different paths. When that information is combined with meteorological data and one of several available algorithms, it's possible to create concentration profiles of that particular target gas in both the vertical and the horizontal, and also provide emissions flux estimates and source strength emission estimates. Some of the work that we've done in recent years, a lot of work was done 3, 4, 5 years ago with waste management, for example, in the United States, quantifying Methane fluxes from landfills. A lot of work has been done with intensive animal feeding operations, dairy farms, pig farms, poultry farms and such, measuring ammonia and methane emissions from those facilities. Of more relevant interest to this audience is the fact that we've done a lot of work with Alberta Innovates and with Shell in recent years, applying this technology for CO2 measurements associated with carbon capture and storage. This is a summary of an experiment we did with Alberta Innovates about 2-3 years ago using proprietary inversion algorithm called residual gas mapping, RGM, from Shell to demonstrate the potential of this technique. In summary, with 6 paths and making measurements over a 1-hour period, the technique was able to locate the source of a gas leak from a gas cylinder within 5 meters, and also to estimate the strength of the source within about 5 or 10%. The source release rate was 0.2 grams per second, and using this technology, the calculated leak rate was 0.21 grams per second, and the center of gravity of the inferred emission location was within 5 meters of the actual location. So, encouraged by this early successful demonstration of the technology, we've been involved in several other field studies with Alberta Innovates and with Shell in recent years. And this is a typical field installation where some CO2 monitoring associated with carbon capture and storage is currently ongoing. So here you see a meteorological station. With this particular mapping technology, it's important to have 3-axis ultrasonic anemometry to give us required information on the standard deviations in the vertical and horizontal wind fields. And that's what we get from this MET station here. This is one of our GasFinder instruments with a reflector in the distance. Because this is a remote location, everything is solar powered, and the data being acquired by this and other instruments on site are being telemetered back to Boreal's factory in Edmonton via a mobile phone data transmission. These are not unusual data, and this graph here demonstrates one of the real challenges in carbon capture and sequestration in trying to detect the presence of CO2 leaks from underground injection. We're really looking for a needle in a haystack. By the time the CO2 leaks from the underground reservoir up to the atmosphere, you're looking for 0.1, 0.2% changes in the atmospheric concentration of CO2. However, this shows that although during the daytime, which are these flat regions here, there's relatively stable CO2 concentrations around about 380 parts per million. Depending on how much air movement there is overnight, CO2 concentrations close to the ground can rise quite significantly because of local vegetation sources of CO2. So here we have 5 successive very quiet nights with significantly elevated levels of CO2. In this occasion here, because there was some wind overnight, you see all that CO2 being involved is dispersed. So this is one of the challenges we have. With CCS projects, you have to have an extensive and reliable set of background data indicating natural diurnal and seasonal variations before you can even attempt to use atmospheric sensing techniques to indicate the presence of leaks from CCS projects. Just briefly give a plug for our sponsor here. Boreal Laser is involved in a number of different research and development programs, and without the assistance of various bodies within the province and the country, it would be difficult for us to make any progress at all. This is a product that was the result of cooperation between the University of Alberta, the National Research Council, ACAMP, in conjunction with Norcada, another small company based in Edmonton. And in this case, ExxonMobil was our industrial partner. And the driving force here was to develop a product based on laser technology to replace an existing ion mobility spectroscopy technology. This was a successful project. The technology is successful, but even more than that, the cooperation that was developed in the process of creating this product has gone on to help Boreal Laser in additional projects that we're now working on. Final slide. The reality is that, as I said earlier, it's not just enough to measure CO2 and CH4 when it comes to greenhouse gases. It's not just enough to be able to measure the small compounds when it comes to leak detection. For tailings ponds, for example, there's a strong interest in measuring the volatile organics and the polyaromatic hydrocarbons. For carbon capture and storage projects, a better way of detecting the presence of leaking CO2 may well be to spike the CO2 with something like perfluorocarbons and then look for the presence of those PFCs in the atmosphere. So currently, and another plug for another of our sponsors here, Andrew Exner from TechTerra will be speaking in the final section this afternoon. We're currently working with the assistance of TechTerra funding to adapt our existing laser technology using quantum cascade lasers, which operate in the mid-infrared region and will enable us to access absorption features of these larger compounds. So this is a significant development. It's a 2-year project, and we're very excited about the results that we'll obtain from that. So that's a brief tour of what it is that Boreal Laser does and what we're planning to do in the future. I'd be delighted to answer any questions you might have.